Yeah, so we know the drill, right? There's problems to work on. Any questions before we get started? Okay. All right, so as usual, if there's questions or comments or anything as we're going through these, speak up. Either use the chat or unmute yourself. I'll try to get through everything, but we'll see. Okay, here we go. All right, so number one, we got this function x minus 1 to the 2/3. Part A is just to evaluate f of 0 and f of 2. That's not too bad. So start off something relatively straightforward. Okay, so plug in 0. All right, let's see. 0 minus 1 is minus 1. So this is minus 1 to the 2/3. And this is going to be 1. All right, take minus 1, square it, you get 1. Take a cube root of 1, you get 1. F of 2. This is even easier. 2 minus 1, that's just 1. 1 to the 2/3 is 1. All right, nothing crazy going on there. Okay, part B. Is f prime of c equal to 0 for some number in the interval 0 to 2? All right, so this is our intermediate value theorem. So intermediate value theorem tells us that, right, we talked about this last week, that if you have a function that spits out one number on one end, one number on the other end, then the function takes all values in between. Right? Here, since on one end our function spits out 1, and on the other end it also spits out 1, then all I can really tell is that it's going to take all the values between 1 and 1. So for all I know, this function doesn't do that. Okay. So no. All right. Questions about that? Okay. Oh, wait a minute. Did I read this wrong? Oh, I did read this wrong. Uh-oh. I read f instead of f prime. Hang on. Okay, part B, sorry, is not talking about intermediate value theorem. It's talking about mean value theorem. So let's just recall what that says. All right, so we have mean value theorem says that if f is continuous on some interval a to b closed and differentiable on the open interval, then there exists some number c inside the interval a to b such that f prime of c is equal to f of b minus f of a over b minus a. Right, that's mean value theorem. Okay, so looking now back at part B, right, the question is f prime of c equal to 0 for some number c in the interval 0 to 2? Okay, so a couple of things we need to verify. Right, first off, is my function continuous on the closed interval 1 to 2, or 0 to 2? And the answer is yes. Right, this is a, nothing crazy going on here. All right, is it differentiable on the interval 0 to 2? Okay, there we're going to have an issue. Right, so if we take the derivative, we're going to find out that it's not defined at x equals 1. Okay, I'm not going to write down what the derivative is, but if we take the derivative and use power rule, we're going to get a negative exponent up here, which means we're going to be dividing by x minus 1, and that's going to be a problem. So it's not defined at x equals 1. Which means it can't be differentiable on this interval, so the theorem doesn't even apply. Okay. So we still have that the answer is no. All right. Okay, so part C, is Rolle's theorem applicable? Rolle's theorem is one of those things that I think is really kind of silly because it just is the mean value theorem. But some guy came along and said, well, what if it's 0? And someone thought that was cool and gave him his own theorem. Whatever. So Rolle's theorem is mean value theorem. Which really just means it's one more thing for everybody to remember, which is why I don't like it. But, you know, have to talk about it. So Rolle's theorem starts off exactly the same as the mean value theorem, but also assumes that f of b is equal to f of a. All right. And if that's true, then this numerator is 0, so this whole thing is 0. And so that tells us that, yeah, there's some c where f prime of c is equal to 0. Right? That's Rolle's theorem. Oops, shouldn't use shorthand. Then there is a c such that f prime of c is equal to 0. Okay. So for the exact same reason as part B, right, we're not differentiable in that interval. Okay. Rolle's theorem does not apply. Okay, questions? All right. Number 2. So we have a function that's continuous on the interval, closed interval 1 to 3, differentiable on the open interval 1 to 3. And we're supposing that f of 1 is 2, f of 3 is 9. What can we say when we apply the mean value theorem? All right. So I wrote the mean value theorem up here. So what we can say then, right, so f satisfies continuous on the closed interval, differentiable on the open interval. So what does mean value theorem say? It says there must be some number in the interval where f prime of that number is equal to this quotient. Right, so we'll just write that down using the numbers that they gave us. Okay, so by mean value theorem, there is a number c in the interval 1 to 3 such that f prime of c is equal to f of 3 minus f of 1 all over 3 minus 1. And since I told us what these things are, we can be more explicit and say that there's some number in the interval 1 to 3 where f prime of that number is 7/2. All right. So that's what the numbers say. Geometrically, what does that say? Right? F prime of c represents the slope of a tangent line. So really what this is saying is that there is some number in this interval, some point where the slope of the tangent line at that point is equal to 7/2. So geometrically, there is some point on the graph of f where the slope of the tangent line
with Scratch, you
is
can
7/2. All right, questions? All right. Okay, so now let's actually do some calculus. All right, so we have this function 2x plus 1 over x squared. We want to find the open intervals where f is increasing and where it's decreasing. Okay, and so we've hopefully seen examples of that in class about how to do this, right? We find the critical points, make our number line, figure out where the derivative is positive or negative, because that indicates where my function is increasing or decreasing. Okay, so the first step is to find critical points. Okay, so to do that, we need to do f prime and set it equal to 0. Okay, derivative 2 minus 2 over x cubed. Okay. I said before, taking derivatives should become second nature, so I'm not going to spend a whole lot of time showing where derivatives come from. All right, this is just x to the minus 2, and then its power rule. Okay, so set this thing equal to 0. All right, the first thing we notice is that this thing is undefined at 0, right, because of this denominator. So we'll need that on our number line. Right. And then where else is this thing equal to 0? Now that we've said, okay, we're not worried about x equals 0, we can solve this thing normally. So how do we do that? Add this term to both sides. And then, or if you want, you can divide by 2 to begin with. But maybe I'll do a little bit more than I did last time. So add this thing to both sides. All right, multiply it over. Divide by 2. Take a cube root. X should be equal to 1. Okay. All right, so that's the first step. Find the critical points. Or let's second thing, make that sign chart. Okay, so we have our number line, right? And on this number line, we're going to put the numbers that we're interested in. Okay, the numbers that we found from critical points or where the derivative was undefined. Okay, so 0 and 1. Okay, so the intervals that we're interested in are -infinity to 0, 0 to 1, and 1 to infinity. Okay, now I need to determine where is the derivative positive, negative, whatever, because then that tells me if my function is increasing or decreasing. So to do that, we choose a test point inside these intervals. So we need to pick a test point. In the designated intervals. And determine if f prime is positive or negative. Okay, and because all we care about is if the thing is positive or negative, I don't need to actually compute it. I just have to know kind of an idea of what's going to happen. All right. So if we choose something over here to the left of 0, meaning we're choosing something negative, and I plug something negative into this derivative, right? The number I get out of there, is that going to be something positive or negative? So if I take something negative and I plug it into x cubed, it's going to be negative again. All right. So then I'm subtracting a negative. So altogether, that gives us a positive inside. All right, so a positive in the interval -infinity to 0. All right, questions about that? Does anybody want me to actually write down the words that I said? Okay, someone sent me a private message saying yes, they want it seen. So, all right, I will do that. Okay, so we choose a test point, right? So we pick something that's very negative. Okay, so pick a number that is negative. Okay, and the one downfall of calculus students is when you're told to pick a number inside of an interval, you always pick the most obvious one. Don't do that. Okay, because what are we interested in? We want to know if the thing's positive or negative. Okay, so pick something that's very representative of the interval that we're interested in. So in this interval, minus infinity to 0, right, these are all the negative numbers. So pick something negative, but, be crazy. Pick, negative 10,000 or something insane like that. All right. Okay. So in the interval minus infinity to 0, we'll choose, let's say, negative 10. All right. F prime of negative 10 is 2 minus 2 over negative 10 cubed. Okay. And if we actually want to compute that thing, you can. All right. But it's going to be positive. Okay, so this is what I mean when I say pick a test point and then determine if your thing is positive or negative. Okay. So hopefully that clears up some of that confusion. All right. In this interval, 0 to 1, okay, we're going to pick something in there and see what happens. So if I choose something inside the interval 0 to 1, it's going to be some fraction that's less than 1. I cube it. I get another fraction that's less than 1. Okay, and then I take 2 and divide it by that fraction. If I take 2 and divide it by a fraction that's less than 1, I get something bigger than 2. Okay, and maybe this is the one that I should actually write down because this is not super obvious. All right, the minus infinity to 0 and 1 to infinity, those ones aren't too bad to see. But this one, maybe I'll actually write it down because we're dividing by fractions, and for some reason that makes everybody crazy. Okay, so in the interval 0 to 1, let's choose 1/2. And then look at what is f prime of 1/2. This is 2 minus 2 divided by 1/2 cubed. All right, I'm going to get 2 minus 2 divided by 1 over 8. So I get 2 minus 16. All right, flip and multiply. And this is certainly a negative number. Okay, so we're negative in this interval. All right. Now, for the interval 1 to infinity, right now we're talking about, nice positive numbers. Okay, so choose a really big positive number to really get a good idea of what's going on. And cube it, you're going to get another really big positive number. 2 divided by a really big positive number is going to be very small, right? Less than 1 even. And if I take 2 and I subtract off something less than 1, well, I'm going to have something positive. Okay, so that one I'm not going to write down. But we're going to be positive there. Okay, so all of that together now gives me exactly where my intervals are for increasing and decreasing. Right? A positive means we're increasing, a negative means we're decreasing. Okay. So I need to move this. All right. So when all is said and done, we can say that f is increasing where? Increasing where this derivative is positive, so minus infinity to 0, union 1 to infinity. right? It's increasing in two places. And it's decreasing on the interval 0 to 1. Okay, questions about this problem? All right. Part B, we want to find the numbers where the relative maximum or relative minimum of f of x occur. Okay, so the thing to remember here is that f when it changes from increasing to decreasing. Okay. And a relative minimum where it changes from decreasing to increasing. Okay, and then I'm going to write this in red because it's very important. These things only apply where the function and its derivative are defined. Okay. All right. That's going to become very important for this particular problem. Okay, so I'm going to redraw the sign chart. We had 0, 1. We were increasing here, decreasing here, increasing here. Okay. All right. So it has a relative maximum when it changes from increasing to decreasing, as long as the function and its derivative are defined at that point. So where does it change from increasing to decreasing? That happens right there at x equals 0. Okay. So f changes from increasing to decreasing at x equals 0. But we're not defined at 0. There's a vertical asymptote there. So we cannot have a relative maximum because it's not defined at 0. That means there is no relative max here. Okay. Now, on the other hand, let me make that purple so it matches the purple thing. On the other hand, right, we're decreasing from 0 to 1 and then increasing from 1 to infinity. So that change happens at x equals 1, and our function is very well defined there. So f of 1 is a relative minimum. Okay. Questions about part B? Okay. All right, so numbers 4 and 5 are examples. So I'm just going to give you the example and then tell you why it's true. And then a good idea would be to go off afterwards and try to come up with your own example. All right, once you see kind of how this works. Okay, so number 4, we want an example of a differentiable function on the interval 0 to infinity that is increasing, but its derivative is decreasing. Okay, so think about what that means. If I want the function f to be increasing, then its derivative better be always positive. Right, we want the derivative to always be positive on this interval 0 to infinity. Okay. And then if we want f prime to be decreasing, then f double prime, right, the second derivative, needs to be negative. On the interval 0 to infinity. Okay, so that's the type of function we are looking for, right? We want a function whose derivative is always positive on 0 to infinity and whose second derivative is always negative. And there are many functions that will do this. One of them is the square root function. All right, square root function on 0 to infinity. Certainly defined, right? I can take the square root of positive numbers. Okay, if I take the derivative, right, I get 1 over 2 times the square root of x, okay, which is still defined, right? The only problem would be at 0, but we're not including 0. We have this open parenthesis here. Okay, if I take the square root of a positive number, I get something positive. And then all I'm doing is just multiplying it by, or dividing by it, and then multiplying by 1/2. Always going to be positive. if I take the second derivative, all right, I'm going to get negative 1 over, and let me just make sure, yeah. Four times x to the 3/2. All right, and again, okay, if I take some positive number, I cube it, I get something positive, I take its square root, I'm still positive, I divide by it, still positive, multiply it by 1/4, still positive, then I throw a negative in front of it. So that thing's going to be negative on this interval. Okay, so this function right here, square root of x, will do the trick. All right. Questions about this one? Okay. All right, number 5, we want an example of a twice differentiable function such that f double prime of 2 is 0, but f does not have an inflection point at x equals 2. Okay, meaning that the concavity does not change at x equals 2. All right, so really what we're looking for is a function where this potential inflection point doesn't actually do the trick, meaning that when we take another derivative, okay, we still get 0. All right, so really what we're saying is we want a function whose concavity doesn't change at x equals 2. All right, and so a clever way to find an example of such a function is to try to draw a picture first. Like draw a picture of a function that doesn't change concavity at 2, and then say, well, what does that have to be then? Okay, so really a function that is always concave down or always concave up will do the trick, as long as this condition is satisfied. Okay, so maybe I'll write that down. So find a function where the second derivative at 2 is 0. But is always concave up or down. This is not the only way to find an example, right? There's other ways to do it. This is a nice way to find an example, right? Because if you're always concave up or always concave down, then obviously you never change, right? If you never change, then you don't have any inflection points. Okay. So your first thought might be, well, what are my functions that are always concave up or concave down? Are parabolas, all right? But if I take two derivatives of a parabola, I'm going to get something constant So I'm not guaranteed that I'm going to get a 0 when I plug in 2. So I need a different kind of parabola. So maybe a quote unquote bigger or wider parabola. And if you think just a little bit, and then look at the function x minus 2 to the fourth, or this is a wide parabola, okay, so that it's always concave up. And if I take two derivatives, this x minus 2 is still going to be there because I haven't gotten rid of it yet. So I'm going to get 0. Okay, so this function is an example of the type of function that they're asking for. Okay. Questions? All right. Okay, number 6. We have some function that's twice differentiable, and we know that f prime of 3 is equal to 0, so 3 is a critical point, and f double prime of 3 is 1. And the question is, does this function have a relative max, a relative min, or neither at x equals 3? Okay, so given these assumptions, let's write down what we know. And I might need some more room, so let me just move this up. Okay, so f prime of 3 being equal to 0 means that 3 is a critical number. Okay, and since it's defined there, right, we can talk about there could potentially be a relative min or a relative max. All right, the only thing we don't know is increasing or decreasing. Okay, so f prime of 3 being 0 means that we have a critical number. F double prime of 3 being equal to 1 means that f is concave up at x equals 3. Right, a positive second derivative means that you are concave up at that point. Okay, so with this information, what can we say here? So concave up whoops. Means that at x equals 3, f kind of looks like this. Right? It has this U shape. And that x equals 3 is a critical number. Altogether, what conclusion can we draw? So this is one of those things where you know you have a critical number, you know it's defined, so there's going to be a min or a max. Yeah, we must have a relative min, right? This picture tells me that, hey, there's probably a relative min there. Right, we're concave up at that point, and it's a critical number, which means that the derivative or the tangent line at that point is horizontal. Okay, so yes, we have a relative min. Okay, this thing is sometimes called the second derivative test. That's not a standard thing, but you might hear that. So if you do hear that, this is what it's referring to. Okay, and because it's not a standard thing, I'm not going to write it down. But if you ever hear somebody say second derivative test, this is what they're talking about. If you have a critical number and you can determine concavity at that point, right? You can determine if it's a relative min or a relative max. Okay. Which means that all that work we did on one of those previous problems with that sign chart and everything, right? We could actually do that without having to make that sign chart. Okay, that's what really this is telling us. Okay, questions about this problem? Okay. So I only have 2 minutes left, so I don't think I'm going to be able to do number 7. All right, so to find where a function is concave up or concave down is exactly the same as trying to figure out where it's increasing or decreasing, except we'll use the second derivative instead of the first derivative. Okay, so I'll say here, follow the procedure for increasing, decreasing, but use the second derivative, right? So find the second derivative, set it equal to 0, you get some numbers out of there, put those on a number line, do your sign chart. Positive means up, negative means down. Okay. And then where the points of inflection occur, right? We said this already, but I'll write it down again. So an inflection point happens when f changes from concave up to concave down, or the other way, concave down to concave up. Okay. So actually doing this problem with this function isn't too bad, because you take 2 derivatives, you're going to get a nice quadratic. And I think, yeah, this thing factors nicely once you take that second derivative. So shouldn't be too complicated. Okay, so we're out of time. I will post this after class. As always, if you have homework questions or questions on these problems, you can send me emails or come see me in office hours. But other than that, have a good rest of your week, and I will see you for the last time next week.